All right, so welcome back. Today we're going to take a look at section 8.2. And in this section, what we're actually going to do is we're actually going to go through the steps of testing a claim that has been made about a population proportion. Okay? So what we're going to do is we're going to describe the complete procedure for testing that population proportion P. Okay? We'll take a look at how hypothesis testing is done with a p-value. We'll discuss the critical value method. And basically what it boils down to is these are two different techniques for doing the exact same thing. They both are a way to test a claim about a population proportion using hypothesis testing. It's just two different approaches. We'll take a look at both of them, and then we'll decide which one we're going to use, right? We can also discuss the potential of using confidence intervals, if you remember those from earlier, as a way. It's not as common to do that, and we definitely won't be doing that here in this section. Okay? So our one objective, though, for this section is to conduct a formal hypothesis test about a population proportion P. Okay? The notation we're going to be using, we're going to have n's and p's and p hats and x's. The n, as it has always throughout the entire idea of stats, is the sample size or the number of trials of that experiment. Right? The P, straight up P, is the population proportion. Right? It is a statement about a proportion of a population that satisfies some criteria that will be set forth in the problem. And then we're going to have our p hat. Our p hat here is going to be our sample proportion. That is going to be the proportion of the sample that satisfy that same criteria. The requirements for this, the necessary pieces and parts to make the math work, are, of course, that you have to have gotten your data from a simple random sample, and that the conditions for a binomial distribution are satisfied. Basically, when we're talking about a population proportion, we're asking a question or measuring a criteria, and we're saying yes or no, yes or no. Does individual number 1 from our sample satisfy this criteria, yes or no? Individual number 2, yes or no? And that's the basis of a binomial problem right there. So the necessary conditions are a fixed number of trials. They're independent. We can think of it as success and failure. Probability of success stays the same, doesn't change. And then our sample is large enough. That is, we have talked to enough people, or we have run the experiment enough times. And the way we defined that was n times p and n times q were both 5 or more. Right? So let's take a look at an example. And we'll start it from the beginning, and we'll run through the entire thing. Okay, so here we go. A researcher claims that less than 45% of US adults use passwords that are less secure because complicated ones are too hard to remember. In a random sample of 100 adults, 41% say they use passwords that are less secure because complicated ones are too hard to remember. At a significance level, at an alpha level of 0.01, is there enough evidence to support the researcher's claim? Okay, so hypothesis testing is where we gather data to determine whether or not a claim that was made about a population parameter can be validated, can be supported with evidence, or where there is enough evidence to not support it. So what we're going to do is we're going to lay out the steps. Now, I've set these things up here over here for us in kind of the order we need them. First thing we do is we need to find the claim in the statement. And then from there, we're going to build our pair of hypotheses. And then we're going to pull the data from our experiment, and we're going to run the test, and then we'll come up with a final answer. Right? All right, so let's look in here and see if we can find the claim. I believe the claim is this. So the population parameter that we're measuring here is the percent or the proportion of adults that use less secure passwords. And the reason they're using them is because complicated ones are hard to remember. The reason they're using those less secure passwords doesn't matter. It's just the claim is about the proportion of adults that are using less secure passwords. Now, the pink that I just highlighted there is the claim written out in words. So what I want to do is I'm going to rewrite that as a statement about a population parameter. So what we're saying here is we're saying that P, the population parameter, is less than 0.45. Less than 45%. As a decimal, 0.45. Less than is a strict inequality, right? So that's going to lead us to a pair of hypotheses. Our hypotheses need to be a null and an alternate hypothesis. Since our claim does not contain equal, that means it is going to be the alternate hypothesis that P is less than 0.45, and then our null is going to be that P is equal to 0.45. Now, as I said in section 8.1, I know, and I'm frustrated by it too, the hypotheses are supposed to be complements. So I know that what you want to write for this one is that P is greater than or equal to 0.45. And I get it, I want to write that too. But the way this textbook, the way the homework, the way the exams, the way this course is set up, we're never allowed to do that. Our null hypothesis is always just a statement of equality. Right. Now I'm going to dig into the problem and look to see if I can find some data. Well, I see some data in there. There's this that tells me that my N is 100. There's this that tells me that my P hat is 0.41. And then with a little bit of algebra, that tells me that X is 41. Remember that P hat is X divided by N. And if we know any two of these values, we can always find the third. Right? We also have an alpha level from the problem. Our alpha level is 0.01. Right? Now, with that data, we should be able to run a test. Now, just so you can kind of get an idea of what's going on here, the test that we're going to run is, according to the claim, the sampling distribution should look something like this, right? And the middle of this should be that P is 0.45, because that's the equality statement from the null hypothesis. Right? Because our alternate hypothesis is a less than, we are going to be running a left tail test. We are going to create a little cutoff here, which is going to be our critical value. The size of this tail over here, because it is a left tail test, that's going to be alpha. So the size of that tail is alpha, or 0.01. Right? We are going to take this data and we are going to place it over here, wherever it belongs upon that horizontal axis. If, when we place that data over there, it falls anywhere in here, right, that is the fail to reject the null region. And if it falls anywhere in that tail over there, if it falls anywhere over here on this piece, that's where we are going to reject the null. Right? Now, how are we going to know where it falls? Well, that's where something called the p-value comes into play. When we run the test is going to return to us something called the p-value. Right? Now, the p-value is, since we're running a left tail test this time, the p-value will be the area that is to the left of our data. Right? So if our data puts us here, then the p-value would be the size of that tail right there. Right? But depending on how the data works here, if the data goes here, then the p-value would just be this little tiny piece. So the test is essentially going to put the p-value the data somewhere on that horizontal axis and tell us how much area is to the left. And if our data ends up here, our p-value will be bigger than alpha. And according to the hypothesis testing, when p is greater than alpha, we fail to reject the null hypothesis. Or if our data ends up over here somewhere, then our p-value will be smaller than alpha. And when p is smaller than alpha, we reject the null hypothesis. So down here where I've got it labeled final answer, what we need to know is we need to know what that p-value is. So we need to run the test. And here's how we're going to run the test. This test, all of the math here can be done by hand, but there's no good reason to do this by hand. So what we're going to do is we're going to run this test on the calculator. So I'm going to pause the video and get the calculator set up. I'll be right back. All right, so I'm back. There's the calculator, and now we need to run this test. So I'm going to go to Stats, and then over to Tests, and then I want to run a 1 proportion z test, which you'll see over there is option 5. Now, the reason this is called a 1 proportion z test is we are making a hypothesis test about one population proportion. There is one sample here. Later, there are two sample, one data set from, I don't know, somewhere, and one data set from, I don't know, somewhere else, and we're going to compare those two. That's that 2 prop z test below it. But this is a 1 prop z test because we have one data set, one sample set of data. That's this business right here, right? And we are running a test. Now, the reason it's called a 1 prop z test is the math behind the scenes is running a standard normal distribution test, right? So I'm going to punch that up, and it's going to ask me for some information. Now, currently mine has some stuff in here because I've used this before. Yours might all be blank, right? But it's asking for several inputs. In this case, it requires 4 inputs. It needs p sub 0. P sub 0 is the equality statement or the equality value from our null hypothesis, which in this case is going to be 0.45. X is the X from our sample data, which in this case is a 41. And again, our sample data, 100. And now the next one is, what test do we want to run? Now, the type of test we want to run is the alternate hypothesis. And our alternate hypothesis is a left tail test. So we got that right there. And then I'm going to go to calculate, press enter. It calculates it for me. And it tells me that my p-value is 0. What does that say? 21, and we usually go like 2 or 4 decimal places. I'm going to go to 407. Right? Now remember, from a moment ago, we were talking about this. This 0.2107 is going to be the size of the left tail when we place our data on the normal distribution over there. So we're looking at something that probably plotted somewhere about here because the size of the tail is about 21%. Now, from the looks of it, you could see that that definitely puts that data in the fail to reject region. You can also just use the comparison. Since p value is greater than alpha, we fail to reject the null hypothesis. Right? So now what does that mean? Well, I'm going to go back up here to what we looked at in section 8.2. And I'm going to go back to this chart right here because this chart right here tells me what to do. Right? So I need to know, well, my decision, the math said fail to reject the null. The claim was the alternate. Those two intersect right here. So that's going to be our answer. Now I need to reword it in terms of the specific problem, but basically I need to say there is insufficient evidence, so there is not enough evidence to support the claim. So I'm going to go back down here and say, I'm failing to reject the null. The claim was the alternate. So my final answer is going to be, there is not enough evidence to support the claim of less than 45% using insecure passwords. And I'm running out of time, so I'm just going to call it pass. Okay. All right, so let's look at what just happened here, because it almost feels counterintuitive. A researcher said that less than 45% of people use passwords that are less secure. We got a sample, and we got 41% in our sample. Well, 41% is less than 45. So you would think that that data then would support what the researcher claimed. But what ends up happening is because we sampled, and the way sampling distributions work, where while, yeah, the middle's 45, but anytime I sample, I'm not going to get 45. I'm going to get numbers that are going to dance around 45, somewhere, sometimes lower, sometimes higher. To really have enough evidence to support that claim, I not only have to be below 45, but I have to be significantly below 45. And it looks like 41 wasn't far enough below 45 for a sample size of 100 and a significance level of 1% to be able to statistically support that claim. So I just don't have enough evidence. Right? Let's take a look at another one and see if we can also make some sense of it. And basically the rest of this section is just going to be redoing the same problem again and again. Someone's going to make a claim, we're going to gather data, we're going to run the test and see what happens. Right? All right, so let's try this one. Oh, but wait a second. I'm sorry, I forgot something. Back up here. Remember how I said the data is going to go somewhere on the x-axis? Do you see this z over here at negative 0.8? That's the data. When we set this thing up as a standard normal distribution with a mu of 0 in the middle and all that business, our z for our data would be negative 0.80. Now, there was a time when this was really important, back when we used to solve these things by doing critical value assessments. But now that we do almost all of them by p-values, the critical values and the associated z-scores here that we're talking about aren't as important. Unfortunately, we still hold on to it a little bit. I will try my best to only pick problems that don't rely too heavily on knowing that or interpreting that, but occasionally something might slip through. All right, so let's take a look at the next one. A researcher makes a claim. A researcher claims that 51% of adults believe incorrectly that antibiotics are effective against viruses. In a random sample of 2,202 adults, 1,161 say antibiotics are effective against viruses at a significance level of 0.10, alpha of 0.10. Is there enough evidence to support the researcher's claim? All right, so I'm going to start where I always start. I'm going to look for my claim. And it looks like the claim is this, that 51% of US adults believe this thing to be true. Right? Now, the fact that it's about antibiotics and viruses, I literally don't care. I want to find out what is the claim about a proportion. And it reads to me that the claim is that the P, the population proportion, is 51. So that means when I set up a pair of hypotheses, a null hypothesis and an alternate hypothesis, that since the claim is a statement of equality, whoops, those shouldn't be equal signs, those should be colons, is the P is 0.51, which makes the alternate not equal to 0.51. The data from the problem, that's our N of 202, our X of 1161, right? And our alpha level of 0.10. Now you may have noticed that in the last problem, we were given N and P hat and we had to find X. And in this problem, they give us N and X and they didn't give us P hat. There's no reason for us to necessarily calculate P hat. It isn't part of what data I need to get the test to run on my calculator. But if you wanted to find P hat, you could. You'd take the 1161 divided by the 2202, and that will be your P hat. Okay. Essentially, because of this right here, we're running a two-tailed test. So the distribution, the sampling distribution, is going to assume that the middle is that 0.51. We're going to gather data. There are going to be two rejection regions because it's a two-tailed test. There's going to be one for low values and one for high values. The size of this tail is going to be 0.05. The size of this tail is 0.05. The reason they're both 0.5 is if the rejection region total size needs to be 10%, and it's two of them and it's symmetric, 5% and 5%, 10%. Then we're going to take our data and we're going to plot our data. And if our data plots here or here, that's the failed to reject. But if it plots out here or out here, then that's going to be the reject the null hypothesis. And again, we're going to determine where it ends up by finding our p-value. And if our p-value is less than 10%, it means it's in one of those rejection regions. All right, so let's go and run the test and see what we get. So back to stat, over to test, one prop z test. Right? My p sub 0 is 0.51 from the null hypothesis. My x is 1161. My n is 2202. I am running a two-tailed test because the alternate is not equal to. I'm going to calculate it out, and it tells me that my p-value is 0.105. Oof. That's bigger than alpha. And if my p is greater than alpha, I fail to reject the null hypothesis. Right? You can see that z-score over there on the calculator screen, 1.61. Right? Remember, the z-score is called the standardized test statistic. The z-score is when they take this data and they turn it into a z-score. They call it the standardized test statistic. It's 1.61. depending on how many decimal places you want, probably 2, so it's 1.62. Okay. Because it's greater than 1, I know that what happened was my data plotted over here somewhere to the right, because z is greater than 0, and in the middle would be z is 0 for our standard normal distribution. So my data plotted over there, and I've got a p-value that is slightly larger, which means I failed to reject the null hypothesis. Right? Now, since the claim was the null, and I'm failing to reject the null, what does that mean? Well, I'm going to go back to my chart. Here's my chart. Okay. The data says fail to reject. The claim was the null. Then they intersect here. And now this is a weird one. Stay with me on this. The result of the test is there is not enough evidence to reject the claim. So I'm going to try to put that into words down here. So what does that mean for this scenario? Well, it means that there is not enough evidence to reject the claim that 51% believe. What was it now? They believe that antibiotics are good for viruses. Boom. Okay. So now, how am I supposed to interpret that? Because I can put words down on paper, but what does that mean? Well, let's go back to what hypothesis testing is supposed to do. I'm supposed to test someone's claim. So this guy's claiming that 51% of people believe this. I'm going to go gather some data. And what I would like to be able to do is I'd like to be able to say, hey, my data says you're wrong. My data says reject the null hypothesis. That's what I want. I want to be able to say there's enough evidence to reject your claim. But I gathered data and I didn't get enough evidence. So I don't have data that supports this guy's claim. What I have is I don't have enough evidence to say he's wrong. And it's like this, a slippery change of the words. I'm not supporting his claim. I don't have enough evidence to say he's wrong, is basically what I'm doing here. All right, we're at 28 minutes. So I'm going to end this video here. I'll make a part 2 and we'll cover the rest of this section. See you all back here for part 2.